So today I'm going to talk about a paper, efficient mean estimation with pure differential progressive of a squares exponential mechanism. This is based on joint work with Sam Hopkins in the previous talk and my advisor at Waterloo, Gaussian Mechanism. And this work also has appeared in a stock 2022. Okay. So at the heart of our result is a new way to design efficient private algorithms, which we call the software squares exponential mechanism, which you just learned about. We specifically applied this method to mean estimation, but we expect that this method can be applied to many other problems as well. So hopefully by the end of this talk, you should be able to learn about this method concretely and maybe use it for other problems as well. Okay, so let's see what is mean estimation. Very informally speaking, you have some vector in RD which is hidden from you. You have some distribution that has mean mu, and you can take samples from this distribution, i.e. samples x1 to xn, and your goal is to come up with an approximation of this hidden vector mu. So there was an open problem in private statistics, and that was whether there exists a polynomial time algorithm for this problem, which requires of these samples and is efficient, as in it is polynomial time in the number of inputs, in the size of the inputs. And we answer to this question up to logarithmic factors in the sample complexity, that the answer is yes. So, and this is basically the most fundamental statistical task you can ask for. If someone comes and gives you a distribution, the simplest thing you can do is just estimating the mean of that distribution. Okay, so let's make this problem a bit more concrete for the sake of today's talk. Again, you have some distribution D that has mean mu. The only assumption we make on this distribution is that it has bounded second moments. That is, its covariance is bounded above by 1. And for the sake of today's talk, we also make the assumption that we have some rough estimate to the true mean, such that this rough estimate has distance at most off with D to the true mean. And our goal is to find some approximation of the true mean. That is, it has distance, say, 0.01 or alpha with very high probabilities, say probability 1 minus beta. And we want this estimator to have to satisfy a pure differential privacy specifically. So to summarize our results, we basically give the first algorithm for this problem, which is simultaneously computationally efficient. It has of the sample complexity up to logarithmic factors and is pure DP. And as a bonus, we also get robustness and sub-Gaussian rates. Note that any 2 out of the 3 the zero datas here were known how to get that before. So like we knew how to get computationally efficient and of the samples, but without pure DP. But all of them at the same time was open. How to get like all of them at the same time. And I'll explain in what follows how to get any 2 out of the 3 as well. So first, so in the rest of the talk, I will first tell you how we can get each 2 out of the 3 first. Then I will try to fix one of them. And this gives us our algorithm, which I will explain in the end. Okay. So there were 3 algorithms known before our algorithm, but as I mentioned, the issue was that each of them had didn't satisfy one of those the zero datas. Okay. So the first one is quite simple. If you are just thinking about this problem from scratch, you're given some samples x1 to xn. You compute the empirical mean. You see that it has unbounded sensitivity, so you can't add Laplace noise to make it private. So what you do is you clip the points into a ball of, say, radius root d, and this bounds your sensitivity. Now you can add Laplace noise to get a private estimator. And if you don't know what Laplace was, what is it? It scales with exponential of minus x. And now that you have added Laplace noise, you're going to get a PUDP algorithm. The issue is that because of this discrepancy between L1 and L2 norm, you're going to add noise that scales with d to the 1.5. So your sample complexity is also going to be off by a factor of d to the half. So you're going to get PUDP. You're going to be efficient, but your sample complexity is going to be off by a factor of d to the half. Another way is using the Gaussian mechanism. It is exactly the same, except you're going to add Gaussian noise instead of Laplace noise. In this case, your L2 error is going to scale with d instead of d to the 1.5. So your sample complexity is going to be O of d, but you're not going to get pure dp anymore. You're going to get concentrated dp, which is qualitatively weaker than pure differential privacy. The third method is using the exponential mechanism. This algorithm was in KSU 20, Chemistry and Oldman. And the idea is that the empirical mean should be close to the true mean in every one direction. So if these are your, if the x's are your data points, and then that point in the middle is the empirical mean should be close to the true mean. Now, in every 1D projection. So, now, if you have some candidate point, like this point, for which there exists one direction, such that on that direction, this candidate point is far from the empirical mean, then you can guess that this point is probably not a very good candidate point for our exponential mechanism. On the other hand, if you have a point such that it is close to the empirical mean on every direction, that point is probably going to be a good point for your exponential mechanism. So there is a way to design, there's a classic way to design score functions for the exponential mechanism. And that is how many of the points in your data set you need to change in order to make your candidate point look bad, look like look like a bad candidate point. Why is this a good score function? Because the sensitivity is going to be 1. So it's nice in that sense, because if you like changing one point is embedded into this definition of a score function. The issue now, if you define this a score function, the score of this point is going to be 0 because you don't need to change any of the sample points to make it look far from the empirical mean. But for the point that is close to the empirical mean, you need to probably change a lot of the points from your samples to make it look far from the empirical mean in one direction. Okay. Now the issue is that this score function, in order to like compute it, it's not clear how to compute this score function. And the naive way is basically by looking into every direction. So you're going to require looking at every direction in d dimensions, which is exponential in d. Also, if you want to run this exponential mechanism, suppose you know the score function for every point. If you want to run the exponential mechanism over the ball of, say, radius root d, you are going to have exponentially many candidates, because the cover over the ball in d dimensions is going to be exponentially large in d. But the good news is that the sample complexity is going to be of d. And as I mentioned, you have two points in this algorithm where you run into exponential runtime. So this algorithm is going to be non-efficient. It requires exponential time. It's going to have the right sample complexity. and it's going to have the right notion of privacy. And as you might have already guessed, our result is that we can get all of these three desideratas using the sum of squares exponential mechanism. Okay. Any questions? Okay. So now, I mean, Sam talked about this a bit, but I'm going to talk about how we can fix this exponential mechanism from previous works, basically. So what were the two problems with this exponential mechanism? First one was that you have an exponentially large set that you want to sample from. So there's a canonical problem here, whether you can do the whether you can run the exponential mechanism for a score function over a domain or not efficiently. The other issue was that even for a single point in your domain, computing the score function requires looking at every direction, and you have exponentially many directions, so it's not clear how to compute the score function. And for this, maybe we can use some developments in robust statistics in recent years. So let's talk about the first one first. How we can deal with the first one. You have some score function. You want to sample from the exponential mechanism. You want to know under what conditions you can do the exponential mechanism efficiently. Fortunately for us, this problem has been studied before, specifically by Vasily Smith and Takurta in 2014, and by Mangubi and Vishnoi in 2021 recently. So if your score function is concave, sorry, I wrote like concave here, I meant the exponential of a score. But if your score function is concave and you have Lipschitzness with respect to the candidates, then there exists a private and efficient sampler. What I mean by private is that the sampling is going to sample, the sampler is going to sample from a distribution that is within multiplicative vectors of the original distribution. So now we kind of know how we can deal with the first issue. We should define some a score function that is concave and Lipschitz. But let's see how we can deal with the second issue. How can we come up with a score function that we can compute it for every point efficiently? This pattern has appeared in robust statistics and high-dimensional statistics before, specifically in robust estimation and in heavy-tailed mean estimation, and in privacy by us and Kothari, Manrang, Lucy, and Wellinger. So maybe we can use some of the ideas in these previous works to define a score function that we can compute efficiently. Specifically, we are going to use the ideas from Gaussian, Mendelssohn, and Hopkins. Okay, so how do these mean estimation, heavy-tailed mean estimation algorithms work? They rely on a definition or concept called high-dimensional median of means, or centrality. What's the idea? You take some samples x1 to xn, you divide them into k buckets, you compute the mean of each of these buckets, name them z1 to zk. Now, if you are in 1D, you can just output the median of z1 to zk, and this is going to be a very good estimator of the mean. It is going to have sub-Gaussian rates. But in D dimensions, it's not clear how to define a high-dimensional median. Fortunately, Kelly gave a talk about centrality and high-dimensional median yesterday, so it's she basically made my job easier. How do we define a high-dimensional median? A point y is a high-dimensional median for z1 to zk if it looks like a median in any direction that you project these points on. So it's going to fall, say, between 40 percentile to 60 percentile on every direction. That's a high-dimensional median. Now, a key observation here is that the true mean itself is going to be a high-dimensional median or central point, and any other point that is close to the true mean is also going to be a central point. So now we have there's an if and only if situation here. So we have basically categorized what it means to be close to the true mean. A point is close to the true mean if and only if it is central. Okay. Now, Hopkins and Chapman-Derry, Flammary, and Bartlett observed that you can define a quadratic program that basically captures this centrality definition. What does this? It's not very important, the details of this quadratic program, but basically what it does is that it looks on every direction v, and it counts how bad mu tilde is in that direction, how not a median that mu tilde is in that direction. So, so if this quadratic program has high value, it means that for the direction v, mu tilde doesn't look like a median. It's like far from being. It's not within 40 percentile to like 60 percentile. Say. So there is also so now we have an equivalent between being close to the true mean, being central, and the quadratic program having low value. Okay. Now, what if the quadratic program doesn't have a low value? If the quadratic program has low value, we know that mu tilde is going to be a central point. We can output mu tilde, we are going to be fine. But what if mu tilde doesn't have a low value? It means that there exists some direction v such that on that direction, mu tilde doesn't look like a median. Now, let's say it's that direction in the picture. So the central point, I mean, you can imagine that the central point is going to be somewhere on that direction. And this direction v points towards the central point. So, and this can be proven. This is very informal. But if you take this direction v, this is going to take you towards the central point. So now we have two situations. If either mu tilde is a central point and you're done, or it is not a central point, but the certificates of non-centrality, that is VIs, can take you to a central point, to the true mean. So now we have an inefficient algorithm. Why? Because we cannot solve the quadratic program. But if we could, we would just basically at each step take the direction v. We would move towards the central point, and this gives us an algorithm, basically, a non-private algorithm. Though we are still not, we still don't care about privacy. But the nice thing about quadratic programs is that we can relax them as semi-definite programs, or degree 2 SOS proofs, basically. Degree 2 SOS programs. So we can, if we relax the quadratic program in a very standard manner, we are going to have the following SCP. It's not important, the details, but the nice thing about this relaxation is that it's going to have every property that the quadratic program had. For example, if it has low value, then the point is going to be central. If it has high value, its certificates are going to take us to the true mean. So we can basically just solve this SCP, and this gives us a polynomial time algorithm. We can, again, move towards the true mean. Now we basically know, let's take a step back. We know how we can deal with exponentially large sets. We know how we can compute the score function efficiently. Now it remains to put the pieces together, basically. So here's the final algorithm. We want to run the exponential mechanism. The goal is to run the exponential mechanism over the set of directions at each step. Okay. So we knew how to find a direction at each candidate point non-privately, but how can we do that privately? We keep the same score function, and instead, oops, oh, there's something wrong with my slides. We add a new condition that v is equal to y. It's not present in my slide, sorry. We add a new condition that v is equal to y. So specifically at each point mu tilde, we are going to compute the score function for the direction y. Now it can be proven that this score function is going to be Lipschitz and concave, so we can run the exponential mechanism for this score function efficiently and privately. Okay. So what is the algorithm now? The final algorithm. We have some candidate point mu tilde. We run the exponential mechanism using this score function SCP valve, and this gives you a direction. You take a step in that direction. You repeat this until you reach a central point. Okay, this is going to take log the initial distance to the central point steps, which was root d. We assume that we are starting from a point that has distance root d, so this is going to take log d steps at most. So yeah. Now the things we did are not specific to this problem of mean estimation. Specifically, if you have any score function that has these properties, that is, high scoring candidates for that score function imply that you have a high utility, you have bounded sensitivity, you have Lipschitzness, you have concavity, and you have a large volume of good points, a large volume of high scoring points, then the exponential mechanism is going to give you a good point with high probability efficiently and privately. And in today's talk, I only talked about the case that we have access to some initial estimate of the mean. But in our paper, we also used the same method theorem in order to solve the case for coarse estimation. That is, from you want to get an estimate that has distance root d. Now, and this can be captured in the method theorem. Don't read that; it's too complicated. Okay. So here's the overall theorem. I will wait until. Okay. So I mean, I didn't talk about robustness in the talk, but it can be easily seen that all of the things we did also preserve robustness. And yeah, here's the final theorem. I will wait until everyone reads it. Say again? No. I'm just waiting. Yeah. Say it again? Yes. So the number of samples you require doesn't matches the lower bound in the fine estimation setting, but in the setting where you want to go from distance r to distance through d, our lower bound and upper bound don't match. So it's an open problem whether we can get rid of that mean d log r term in coarse estimation. Any questions?
So to do this, you need to like run the exponential mechanism many times.
Log d times.
Okay. You can't like express it as like one single sample.
Oh, like one shot. I mean, there are some ideas. Maybe we can do, but it's not in the.
Yeah, really, I was wondering about the same thing. So the recipe that Sam presented was kind of a one-shot thing, and also the meta theorem, right? But there was a previous exponential mechanism, and then this recipe for doing
I mean, currently we don't know.
Can you explain
what?
Where did that switch happen? What you presented?
Oh, it's just that we don't. I mean, if we don't care about privacy, I think we don't really know. I mean, Sam should probably know the answer there. But even if we don't care about privacy, there is no SOS algorithm to just one-shot thing for. I think. Right?
I think there is a one-shot robust SOS algorithm, and the SOS proofs are super complicated for some reason. Like this is for some technical reason, but I think there was probably an avenue that does it in one shot. And at some point we hit a fork in the road, and there was 2 weeks to go to a deadline, and it was like, let's write the easy version of this algorithm. But I think there should be a one-shot version of this. We never pushed hard on it.
Yeah.
Maybe if I can just elaborate. So you presented the earlier pure DP inefficient algorithm, which wasn't instantiation of exponential. But the final algorithm you got wasn't obtained by just applying the SOS recipe.
Oh, right.
So you can view it in that way. If you take, so let me tell you a slightly different non-SOS exponential. Slightly different way. It'll have log d rounds of exponential. In each round, it'll take a current guess for the mean, and it'll find a direction where that guess is bad and update the guess.
Got it. And so that's the thing that you're applying the SOS recipe.
So we'll have an exponential mechanism that does that. It just looks for a direction where there's a lot of samples in that direction. And we'll apply the SOS exponential mechanism recipe to that guy, and we'll do it log d times. And somehow, just because that's a much simpler exponential mechanism, like the privacy and utility proofs for that guy are very simple. And the privacy and utility proofs for the one-shot exponential mechanism are more complicated.
Got it.
And because those proofs are simple, we can do them more easily in this way.
Thank you.
Any more questions? Thank you. Okay. So it's an open problem whether we can get rid of that mean d log r term, which I mentioned here. So what's the conclusion? We give the first private efficient algorithm for mean estimation. It has both the sample complexity. We basically connect robustness and privacy together. We also get robustness of Gaussian rates. And another open direction is where else we can apply SOS proofs, SOS to pure DP estimation, sorry, and more connections maybe between privacy and robustness. See where else we can use tools from robustness to come up with algorithms in privacy or vice versa. Okay, that's it.